here are your notes on the kinematic equations. The first kinematic that we'll look at is displacement with constant acceleration. This is displacement that's dependent upon acceleration, average velocity, and time. So you're really not breaking up the velocities here. You're going to keep it one entity, VF and VI. And a little bit more, I would like you to add constant right here. The equation that you're going to use for this is delta x equals 1/2 quantity VI plus VF times delta t. So let's try this into a problem. This racing car reaches a speed of 42 meters per second. Once there, it begins a uniform negative acceleration by using a parachuting and braking system, which makes the car come to rest 5.5 seconds later. Calculate the distance that the car traveled while braking. So looking at that problem, we know that we have some givens of an initial velocity of 42 meters per second. We also have a final velocity of 0 meters per second. Oops, sorry. And we have a time of 5.5 seconds. Reading the problem again, you can find out that it's asking you to calculate the distance, how far. Really, yeah, it should say displacement there, but this is the problem. Okay, so from that, what we see here is that there isn't like a delta x. There is the VI and the VF. So we want to use the delta x equals 1/2 quantity VI plus VF times delta t equation. We don't need to rearrange anything because the variable that we are trying to solve for is already isolated. So let's just simply plug in our numbers here. Please get your calculators out. 0.5 times 42 times 5.5. 0.5 times 42 times 5.5. What do you guys see in your calculators? Write that calculator answer down, please. Take a second right now, calculate it out. In your calculators, you should see 115.5. Looking over here at your givens, you only see 2 for your final answer, and that 5 rounds the 1 up. Therefore, your final answer becomes 120 meters. 120 meters. All right, let's look at the next one here. The next one that we have then is final velocity and time. Final velocity and time. So this one's going to depend upon initial velocity, acceleration, and time. Notice how displacement is not considered here. So you don't want to see a delta x in this equation. Therefore, it reads VF equals VI plus A times delta t. VF equals VI plus A times delta t. Our third kinematic is listed the same as our first, but it is different. The difference is there is no final velocity written here. So there's no VF. There is a VI, but there is no VF. Personally, this is the one that you're going to use and use and use and use some more. This equation is delta x equals VI times delta t plus 1/2 A times delta t squared. And I'm putting that squared inside there, guys, just to kind of implement or imply that it's only the time that's being squared. This is also used for finding the displacement of an object that has reached a certain speed or has come to a stop. So in other words, there's no final velocity. It's equal to 0. Let's try a problem out here. It says an airline plane is at rest at one end of a runway. It soon begins a uniform acceleration of 4.8 meters per second squared for 15 seconds before taking off. Calculate the speed at takeoff and calculate how long the runway must be in order for the plane to take off. So from this, we know that we have an initial velocity of 0 meters per second. Meters per second. And we also have an acceleration of 4.8 meters per second squared. We have a time of 15 seconds. And we are trying to calculate out a final velocity in meters per second. There I go again. Sorry. And we are also trying to figure out how long this runway must be in meters. So the first kinematic you want to use is VF equals VI plus A times delta t. VF is what we're trying to solve for, and units look okay, so we have 0 plus the quantity of 4.8 times 15. So in your calculators, please put in 4.8 times 15. 4.8 times 15 equals, write down your calculator answer, please. Calculator should read 72. Looking over here at your givens, you only want 2 sig figs, so therefore your final answer is 72 meters per second. All right, to solve for the second half of the problem of how long must this runway be, this is going to be our third kinematic equation. We do not need to rearrange. The variable we're trying to solve for is already isolated, but check this out. Wow. How come we can get rid of just that, guys? Stop and look at that. Don't like just go into the rhythm of it. Actually think. Your VI is 0, so we can just hack that off because anything times 0 is 0. So therefore, we have 1/2 times A times delta T squared. And you can't just say, oh, I'll take half of 72 because it's T squared. So you need 15 squared times 4.8. Take half of that answer. So 1/2 times the quantity of 4.8 times 15 squared equals, okay, so 15 squared equals times 4.8 equals times 0.5 equals, step by step by step by step by step. Your calculator answer should be 540. And you only want 2 sig figs, so your final answer is 540 meters. Cool. All right, moving right along, guys. Final velocity without time. So now this kinematic equation will have all variables except for time. So the equation here is VF squared equals VI squared plus 2A times delta X. Once again, there is no time present. Time is not a factor in this one. What you need to be careful for is, like, if you're going to square root one side, you got to square root the other side on these problems. So let's try that here. It says this mom started from rest, but soon began to push the stroller while uniformly accelerating at a rate of 0.500 meters per second squared. Calculate the velocity of the stroller after traveling a distance of 4.75 meters. So it says this mom started from rest. VI, 0 meters per second. Also, your acceleration, 0.500 meters per second squared, and your displacement of 4.75 meters. Calculate the velocity of the stroller after traveling this far. So that would be your final velocity in meters per second. I'll get it right one of these times, I promise. Okay, so the equation you want to use here is the kinematic that does not have time in it. That would be your VF squared equals VI squared plus 2A delta X. Now we want to just have VF, so we need to square root both sides. So VF equals the square root of VI squared plus 2A delta X. Plugging this in, our VI squared is 0, so nix it. That would be 2 times 0.500 times 4.75. Before you even pick up your calculators, think first, guys. What is 2 times 0.5? Times that by 4.75. Okay, so that's 4.75, right? So then your calculator is the square root of 4.75. That's all you need to input. So the square root of 4.75. What does it say, guys? 2.18 is what you should be seeing. Looking at your sig figs, 3 is the number of sig figs that you want. Therefore, your final velocity is 2.18 meters per second. All right. Next thing, here's just a quick summary of your kinematic equation. So like maybe this is a page that you want to print out, cut it out, post it, paste it, put it in your binder, whatever. But it's just summing it up of all of your equations. Now some of them is saying, okay, so if you start from rest, in other words, just get rid of VI and rewrite the equation. That's all they did. I mean, don't even look at that right side if you think it's going to be confusing. All they did was get rid of the VI because you're starting from rest. Okay, so free fall. Objects in free fall undergo a constant acceleration. A changing velocity implies an acceleration. We're going to disregard air resistance for now. We will be talking about it though. All objects drop near the surface of the earth fall with the same constant acceleration that is given the symbol of g. It is not gravity. It is acceleration due to gravity. It is free fall. It is not G as in gravity equals. Gravity is a force, not an acceleration. So please don't say gravity of 9.81. No such thing, guys. Okay? So this is really the big thing that you need to know on this slide. 9.81 meters per second squared. And then assess direction with it. Okay, so check this graph out here. You threw this ball up into the air at point A, and then it came to rest and changed directions, crossed over the x-axis, changed directions, then it came back down. But look at what the time interval is doing. Okay, the time interval is constant and displacement is clearly decreasing, and then displacement is clearly increasing as that same time interval is going on. So you can see that this one actually is showing slowing down, and this one is showing speeding up on this side. Why is that? Because of the effect of gravity, not because of gravity at 9.81, but the effect of gravity makes the object travel faster. So here you could say that you are, at A, you are slowing down in the positive direction, and here at C, you could say you are speeding up in the negative direction. Makes sense? Coming back down, negative direction? Cool. All right, so this is just a closer look of that. Take a second, read through it. You have it on you. Okay, so once again, one point I want to make, the whole path, due to the gravitational force, you have a constant 9.81 meters per second squared. It's due to the gravitational force. It's not due to gravity. Okay, so now your x's become y's and your a's become g's. So it's the same exact four kinematic equations that we just did all those sample problems on, but now instead of an x, you're going to write a y, okay? Instead of an a, you're going to write a g. And your g will always be 9.81 meters per second squared. So remember to write this as one of your givens. Because it's not going to come on and say, hey, by the way, remember to write this down as a given. Okay, so once again, same for kinematics. It's just that a's become g's and x's become y's. So let's try this problem out here together. Jason strikes a volleyball so that it moves with an initial velocity of 6.0 meters per second straight upward. If the volleyball starts from 2.0 meters above the floor, calculate how long it would be in the air before striking the floor. So it's coming back down, guys. It's coming back down. It's coming back down. It's negative. It's coming back down. Okay, so you have an initial velocity of 6.0 meters per second. You have your gravity, which is your acceleration due to gravity, of 9.81 meters per second squared, but how is it traveling? Down, so it's negative. And you have your delta y, not delta x, but delta y, of a negative 2.0 meters. So from that, you want to figure out your delta t, and your delta t into your seconds. Use your vf squared equals vi squared plus 2g delta y equation. Rearranging this and plugging into it, you're going to get, I want you to try that, okay? You're going to get a final velocity of negative 8.7 meters per second. Once you get that final velocity, then use your second kinematic equation to figure out your how long it will take. Rearranging that equation will give you Vf minus Vi all over G will equal delta T. Take a second, plug in Vf that you just solved for, minus your Vi divided by a negative 9.81 will give you a positive, and your positive will give you a final answer of 1.5 seconds. Will give you your delta T, okay? 1.5 seconds. All right, so that wraps up this section on your kinematics and your free fall acceleration. That is it for 1D motion. The next videos will go on to 2D motion.